Today, we are looking at the qualitative analysis of carbohydrates. So, we'll start by looking at the various classification of carbohydrates. So, basically, carbohydrates can be classified or put into four main groups. So, we have the monosaccharides, disaccharides, oligosaccharides, and the polysaccharides. The monosaccharides are simple sugars, and we have aldoses, so which are simple sugars containing an aldehyde functional group, and ketoses, which are simple sugars containing a ketone functional group, as examples of monosaccharides. And for the aldoses, these are the examples that we have over here, and also for the ketoses, these are the various examples that we have here, and I will encourage you to go through the table to see the various examples for each of the sugars over here. Now, so the next is disaccharide. So disaccharide is basically two monosaccharide units. So we can also group them into reducing sugars or reducing disaccharides and non-reducing disaccharides. For the reducing disaccharides, we have maltose and lactose, and for the non-reducing disaccharides, we have sucrose. Oligosaccharides basically is made up of 3 to 10 monosaccharide units, and we have raffinose, we also have starchose, and we also have fibascose as examples of oligosaccharides. Polysaccharides, they are made up of more than 10 monosaccharide units, and we have homopolysaccharides and heteropolysaccharides. So under the homopolysaccharides, we have these examples, and also under the heteropolysaccharides, we also have these examples. And again, I will encourage you to take your time and go through the various classification of carbohydrate and their examples. Reducing sugars. Reducing sugars are sugars that are capable of acting as reducing agents. And in this reaction, the reducing sugar is oxidized to carboxylic acid or carboxyl group or carboxylate anions. Also, reducing sugars act as reducing agents in alkaline medium such as Benedict reagent and alkaline copper tartrate reagent. So these are some of the reagents that reducing sugars can act as reducing agents because of their alkaline medium. So what you also have to notice that monosaccharides can be divided into two groups. So we have the aldoses, which have an aldehyde functional group, and ketoses, which have a ketone functional group. And also ketoses must first tautomerize to aldoses before they can act as reducing agent. Non-reducing sugars. Non-reducing sugars are sugars that are not capable of acting as reducing agents because they have no free aldehyde or ketone functional groups and do not get oxidized. Example is sucrose. So now let us look at the qualitative test of carbohydrates. We'll start by looking at the Benedict test. So first of all, what you have to notice is that the Benedict test is used to detect the presence of reducing sugars. The principle of Benedict test. Reducing sugars under alkaline conditions tautomerize to form enedios, which are powerful reducing agents. The enedios reduce cupric ions to cuprous form, which is indicated by the formation of a brick red precipitate. So this is just a reaction explaining the principle behind the Benedict test. So as we can also see from this result, a blue color indicates a negative result for a Benedict test. A green or yellow precipitate indicates traces of reducing sugar, and an orange red precipitate indicates moderate amount of reducing sugar, and a brick red precipitate indicates large amount of reducing sugar. To prepare the Benedict reagent, we need copper sulfate pentahydrate, we also need sodium carbonate, and we also need sodium citrate. So these are the chemicals used to prepare Benedict reagent in their required masses. So what you also have to note is that the copper sulfate pentahydrates make available the cupric ions, and the sodium carbonate makes the medium alkaline, and the sodium citrate complexes the cupric ion being produced by the copper sulfate pentahydrate. The next test is Molisch test. The Molisch test is used to test for the presence of carbohydrates. Let us look at the principle. Carbohydrates, when treated with concentrated sulfuric acid, undergo dehydration to give sulfuric derivative. These compounds condense with alpha naphthol to form purple or a red-violet colored complex. What we also have to note is that pentose sugars will yield sulfurous, while hexose sugars yield 5-hydroxymethyl sulfurous. And this is a test result showing a Molisch test for carbohydrate with fructose, glucose, sucrose, and starch, which are all carbohydrates, giving a positive test result, and distilled water, which is used as a control, giving a negative result because it's not a carbohydrate. Anthrone test. Anthrone test is used to test for the presence of carbohydrates. Principle. Carbohydrates, when treated with concentrated sulfuric acid, will undergo dehydration to give sulfurous derivative. And this compound condense with anthrone to give a blue-green colored complex. What you also have to note is that pentose sugars yield sulfurous, while hexose sugars yield 5-hydroxymethyl sulfurous. So these are the positive results for anthrone test. Seliwanoff test. The Seliwanoff test is used to distinguish ketoses, so which are ketone containing sugars, from aldoses, which are aldehyde containing sugars. So what it means is that it gives a positive test to ketoses and negative test to aldoses. The test relies on the principle that when heated, ketoses are more rapidly dehydrated than aldoses in the presence of concentrated acid. And what you also have to notice is that the Seliwanoff reagent consists of concentrated hydrochloric acid as a dehydrating agent and resocinol as a condensation reagent. So this is a test result for Seliwanoff test for ketoses. So as you can see from here, we have fructose, which is a ketose monosaccharide, giving us a deep cherry red, indicating a positive test result. And we also have a sucrose, which is also giving us a cherry red color indicating a positive result, and we also have our doses and our control using distilled water giving us a negative result. So this is a positive result for Seliwanoff test, and these are the and these are the negative results for Seliwanoff test. Test principle. Ketohexosis, which assists carbon monosaccharide with ketone functional groups on treatment with hydrochloric acid, dehydrates rapidly to form 5-hydroxyl methylfurfural, which on condensation with resocinol gives a cherry red colored complex. So these are the cherry red colored being seen over here, indicating a positive test result for Seliwanoff, and these are a faint pink red or no or like no color change, indicating a negative test result for the Seliwanoff test. Tollen's test. The Tollen's test is used to determine the presence of aldehydes, and it gives a positive test for aldehydes, aromatic aldehydes, but not for ketones, except alpha hydroxy ketone functional groups. So let us look at the test principle. In the presence of Tollen's reagent, aldehydes are oxidized to carboxylic acids, where silver is reduced to metallic silver, which is deposited as a thin film on the surface of a glass test tube, as seen in test tube B and test tube C. So what it means is that test tube B and test tube C indicates a positive test result for Tollen test, while test tube A indicates a negative test result. So let us look at the Tollen reagent. The Tollen reagent consists of a solution of silver nitrate, ammonium hydroxide, and sodium hydroxide to maintain a basic pH of the reagent solution. And its chemical formula is this. And the Tollen reagent also contains a diamine silver 1 ion. So this is a diamine silver 1 ion over here. And what we have to note is that although this ion is a weak oxidizing agent, it oxidizes aldehydes to carboxylate anion or carboxylic acids. And as it does this, silver is reduced from the +1 oxidation state to metallic silver, which is deposited as a thin film on the surface of the glass test tube. And as explained earlier over here, so test tube B and C indicates a positive test for the Tollen reagent. And this is a reaction explaining the principle behind the Tollen test. So let's see how to prepare Tollen reagent. It's basically involved 2 steps. The first step, sodium hydroxide is added to silver nitrate to produce light brown precipitate as silver oxide. So as you can see, so this is our silver nitrate reacting with sodium hydroxide to produce silver oxide, which is seen as a light brown precipitate, and sodium citrate and water. So the second step is concentrated ammonium solution is added to the silver oxide until it completely dissolves to form a diamine silver ion complex. So this is the Tollen reagent, which is also a diamine silver ion complex. The next step is fermentation test. Fermentation of carbohydrates by microorganisms like yeast result in the production of acid or gas or both. The production of acid lowers the pH of the test medium, which is detected by the color change of the pH indicator. The production of gas is detected using the Derham tube. And what you also have to note is that 5% yeast is the microorganism that we are going to use in the fermentation test. Ammonium molybdate test. Ammonium molybdate test is used to test for phosphate containing carbohydrates. So let's look at the test principle. Phosphate containing carbohydrates, when acidified with dilute acid such as dilute nitric acid or sulfuric acid and heated with ammonium molybdate reagent, will produce an inorganic phosphate precipitate as a yellow ammonium phosphate molybdenum. So this is the inorganic phosphate precipitate seen over here as a yellow ammonium phosphomolybdate. And this is also the reaction explaining the test principle behind ammonium molybdate test. Barfoed test. The Barfoed test is used to 1. Test for reducing carbohydrates, and 2. Distinguish reducing monosaccharides from reducing disaccharides. And what you also have to note is that the test is based on the reduction of copper 2 acetate to copper 1 oxide to form a brick red precipitate. So now let's look at the Barfoed reagent. So the Barfoed reagent is made up of copper acetate in a dilute solution of acetic acid. So the test principle. Reducing monosaccharides are oxidized by the copper ion in solution to form carboxylic acid and reddish precipitate of copper 1 oxide within 1 to 3 minutes. The reducing disaccharide in an acidic medium cannot reduce the cupric ion to copper oxide or to the brick red precipitate quickly, but at a slower rate of about 5 to 12 minutes. So these are the positive tests for Barfoed reagent. These are the negative tests. So we have xylose, glucose, and fructose, giving us a positive result for the Barfoed test, and we have lactose and sucrose, giving us a negative result. So these are the various chemical equation or reaction explaining the principle behind the Barfoed test. So if you look at the first reaction over here, the reducing sugar reduces the cupric ion in the Barfoed reagent to cuprous oxide, which is seen as a brick red precipitate. And what you also have to note is that the reducing sugar is also oxidized to carboxylic acid. Now let us also look at the second one. The second one is also the same. Then the second reaction is also the same as the first reaction, where the reducing sugar reduces the cupric ion in our reagent to cuprous oxide, which is precipitate and seen as a red brick color over here in our test solution. And at the same time, the reducing sugar being oxidized to carboxylic acid over here. The third reaction. From the third reaction, we can see that the reducing sugar, which happens to be D-glucose, reduces the cupric ion in the test reagent to cuprous oxide, which is precipitated out as a brick red color as seen over here. And also the reducing sugar D-glucose over here is being oxidized to D-gluconic acid over here. So what you have to note is that whenever a reducing sugar reduces cupric ion to cuprous oxide, the reducing sugar in itself is being oxidized to carboxylic acid or carboxylic anion. So let's see how Barfoed tests distinguish monosaccharides and disaccharides reducing sugars, or how the Barfoed test is used to distinguish monosaccharide reducing sugars and from disaccharides reducing sugars. So first of all, what we have to note is that reducing monosaccharides are stronger reducing agents than reducing disaccharides. And two, the acetic acid in the Barfoed reagent creates an acidic medium which is unfavorable for reduction. And since the acidic pH medium created by the acetic acid in the reagent is unfavorable for reduction, the reducing monosaccharide, which are stronger reducing agents than the reducing disaccharide, will react in about 1 to 3 minutes to reduce the cupric ions in the copper acetate to cuprous oxide. However, the reducing disaccharide will take a longer time of about 5 to 12 minutes, having first to get hydrolyzed into the acidic solution before reacting with the cupric ion in the copper acetate to form a brick red precipitate of copper 1 oxide. So this is how the Barfoed test is used to distinguish monosaccharide reducing sugars from disaccharide reducing sugars.